In lesson 4, we're going to look at more with domain and range. So the first thing is just a refresher of what domain is. And remember, domain are all of the input values or the x values. So domain, let me just write this up here, represents all of the x values or the input values. And then range represents the y values or the output. So when we're looking at domain, we can also find domain algebraically. So when we look at finding domain algebraically, which would be all three of these, we have to consider a couple different things. So this is to find domain algebraically. So the only time that you would have a function where the domain isn't all real numbers is if they give you some kind of function that has a square root, because if you remember, you can't take the square root of a negative number. So whatever the stuff is underneath, so I'm just going to put stuff under the square root, that stuff can't be negative. So that means if you were to solve it algebraically, what you would do is you would take that stuff and you would set it greater than or equal to 0 so that you're only making it positive. Another scenario is when you have a fraction. So let's say we have a numerator over some denominator. You cannot have 0 in the denominator. If you divide by 0, it's undefined. So whatever is in the denominator has to not equal 0. So the denominator does not equal 0. That's how we would figure out the domain of something like this. And then the last one we won't talk about quite yet, but let me just get it in here since we are talking about domain. It's when we talk about logs, which will come later on in the year. But whenever you take log of something, so like log of, let's say, this stuff again, you can't take log of 0 or a negative number. So what you would do is you would take whatever is inside of the log and you make sure that it's greater than 0. And then also keep in mind whenever you're finding the domain, so this would be algebraically, but graphically, so if you wanted to find the domain graphically, what you do is you just move across the x-axis and see what x values you have. So we would look at x values and move across the x-axis basically from left to right. And then there's one other thing when we're talking about domain, which is called the relevant domain. And this is really when you get into word problems or application problems. And let's say you have some kind of function that's modeling the cost of something. And let's say it's like a linear function. So linear functions would always be a line and the domain would be all real numbers. But if you have a function that's modeling the cost of something, the input might be like the number of items, and it wouldn't make sense to say that the number of items are going to go from negative infinity to positive infinity, including all the decimals and negative numbers. So we would have to restrict that domain to just whole numbers because the domain is talking about number of items. So it would make sense to say you have 0, 1, 2, 3, 4, and so on items. So let's go ahead and we'll just break that down. So if we had a cost function where x represents the number of items, we would restrict the domain to whole numbers, even though the function itself might be something that can go all real numbers. So then the last thing here is looking at range. So for range, it's a little more difficult to look at algebraically because you really have to look at, well, what's your domain? What does that minimum domain value give you as an output for your range? what does the maximum input value give you as your range. So it's much easier to look at range graphically. So that's how we're going to look at it. So graphically, just means that you're going to look at the y values and you're going to move up and down the y-axis to see them. And if you were able to use a calculator, what you could do is you could put the equation into your calculator and then you can look at those output values in the table. So again, it's going to be hard to do this without a calculator, so we're really just going to look at the graph. So looking at some examples here, this example here, we want to find the domain and the range. So the domain, remember, is moving left to right across the x-axis if we're looking at it on a graph. So if you look at this function, as I move from left, this has an arrow, so it's going to start at negative infinity. It's going to keep going to the left. And then it appears that the y-axis is actually going to be an asymptote. If you look, x equals 0 is this line. My graph never crosses this. It's going to keep getting really close to it in both directions, but it will never cross it. So that means at 0, I don't have any function. I don't have any outputs at 0. So that means 0 is not part of my domain. So I'm going to stop the domain at 0, meaning I'm going to use soft brackets. It's going to get really, really close to 0, but not actually touch it. And then I'm going to pick back up at 0 on the right side, and it's going to keep going. I still have graph as I keep going to the right. I still have output values, so that means it's going to go to positive infinity. So we have these two different pieces, and usually when you have two different pieces like this, you use that union symbol. It just means that both of these are included in the set for the domain. If you just put a comma between them too, that's fine. And then for the range, so again, we're going to go from bottom to top along the y-axis, and again, I see this asymptote here at y equals 0. So the range starts out at negative infinity. This graph is going to keep getting smaller and smaller. And it stops at y equals 0. But then it picks back up and goes to positive infinity. So 0 to positive infinity. So then that's it for that. And just remember, an asymptote is just like this imaginary line that the graph gets really close to, but it doesn't actually cross. So that's helpful when you're seeing the domain and range, that you don't include that asymptote line. You use soft brackets, though, to represent that the numbers get close to 0 on the left-hand side, they get close to 0 on the right-hand side, but they don't include 0. So that's why I have to break it up into two sections. All right, the next example on the graph, we have, again, domain and range. So domain, this time I don't have arrows. So whenever you don't have arrows, that means your graph isn't going to be negative infinity to positive infinity because you don't have any way to represent that it keeps going. So if you look, the graph goes from negative 2 to 2 for x values. So you have to decide, can I include these numbers though? So at negative 2, I have an open circle. So that means I can't include it. When I get to 2, well, first of all, let's stop at 1 here. See how 1, there's an open circle? So I should stop at 1, kind of like what we just did in the last problem where we stopped at 0. But since I have a value up here filled in for 1, that means that this function does have an output if you input 1. So in this case, it's okay because I have that point above it. And then I go to 2, and I see up here I have an open circle. But since I have a filled in point here, that means, again, there's an output for the input 2. So that means now I can actually include 2 because there's some output. Where the negative 2, I didn't have any output value. I just have, it gets really close to negative 2 for the x values, but I don't have an output at x equals negative 2, which is why I did the open bracket. So then the range, you're going to look at the y value. So the lowest y value starts here at 1, And again, we can't include it, but I can include it because I have a filled in circle, so I can do a hard bracket around 1. And then we go all the way up until the highest y value, which is up at 4. Because of this point, I can include 4, where this point wouldn't allow me to include 4. It would get really close, like 3.99999, but it wouldn't actually include 4. But I can because I have it over here. So it's going to be a square bracket around 4. So that's it for that. And then the last thing is just going to be looking at these examples algebraically. And notice that we're only going to find the domain because, like I said, it's the only way that you guys are going to need to know to find the range is going to be on a graph. So we're going to stick with that for domain and range. And then domain, we're also going to look at algebraically. So this is where, for domain algebraically, you're just going to assume that it's all real numbers unless you have one of those restrictions. So you can assume the domain is negative infinity to positive infinity unless you have one of the restrictions. Or a piecewise function. So that graph that we just looked at is something called a piecewise function, which we'll be looking at later, where different parts of like lines were graphed and there was like restrictions involved. So that's when things are not going to be as straightforward as negative infinity to positive infinity. So for all other cases though, like if you have a polynomial graph or a linear or quadratic, your domain is just going to be negative infinity to positive infinity. The only things you have to watch out for are those square roots, fractions, and if they're logs. So for this first one, we have a restriction because I have a square root. I know that we can't have x plus 5 be a negative number. So the restriction is that we cannot have a negative number. So this x plus 5 cannot be negative. So what that means is I take x plus 5, if you remember that was the stuff, and I take the stuff and I make it greater than or equal to 0 because it can't be negative. And then I just solve it. So we subtract the 5. So we get x must be greater than or equal to negative 5. So the domain would start at negative 5, and it can include it because I have the equals bar. And x has to be greater than it. So x is going to be any number bigger than negative 5. So you could write the domain this way or using the interval notation. So this example over here, we look at it and we see a fraction. So that means the denominator cannot equal 0. So what I do is I take the bottom and I set it not equal to 0 because it can equal 0. And then you just solve it like a normal equation. So I can factor this. It's a difference of perfect squares. So when we split it, we get x plus 3 does not equal 0. X minus 3 does not equal 0. Bring over the 3. X does not equal negative 3. X does not equal positive 3. So that means the domain, you could either say is all real numbers except for negative 3 and 3, or you can say in interval notation, you would start at negative infinity, you would stop once you get to negative 3 because you can't include it, but then you would pick back up at negative 3 and go to 3, and then you would pick back up at 3 and you would go on till negative infinity, or till positive infinity. So let me just show you that like on a number line so that makes sense. So basically, you have the points negative 3 and positive 3 that can't be included. So you want to represent this situation. Everything except for negative 3 and positive 3. So if you look at my first interval here, I went from negative infinity to positive, or to negative infinity to negative 3. I picked it up, that's the union. Then I started up at negative 3 to 3. Then I picked it up and I went from 3 to infinity. So since there's 3 sections, that means you have to have 3 intervals. This one over here, I had -5, and it was a solid circle, and x needed to be greater. So I only have one interval because I have one section on the number line. So if it helps, draw the number line so it's easier for you to see the intervals, because sometimes they're kind of hard to write in your head. So then let's look at just these last two. So this one here, we have a fraction. So again, the denominator cannot equal 0. So x minus 3 does not equal 0. Bring over the 3. So the domain, let's look at this on a number line. I have 3, I cannot equal 3. So I have everything on the left and everything on the right of 3. It's just everything except for 3. So that means when I go to write this in interval notation, negative infinity, I stop when I get to 3, open circle because I don't want to include it, but then I pick back up on 3 and go to positive infinity. And then the last one here, we have a square root, so this cannot be negative. So that means you take that and you're going to set it greater than or equal to 0, because basically you have to make it so that it's positive or equal to 0. It just can't be negative. You solve it, we get x is greater than or equal to 2, so you could say the domain is that, but typically we write our domain in interval notation. So if you look at this on a number line, we would have 2, a filled in circle there, and x is bigger than that. So you'd shade to the right. So we would be, for the domain, starting at 2 with a square bracket, going to positive infinity. And that would be it for that.